Welcome to this explainer. Today we're taking a really fascinating research paper from Unijui University and turning it into a clear, structured guide on how to absolutely eliminate the headache of manual blockchain deployment. If you've ever tangled with the complexities of enterprise blockchain networks, well, you know exactly the kind of headache I'm talking about. We're looking at a brilliant, model-driven approach that completely reimagines how we specify, validate, and deploy Hyperledger Fabric networks. Let's get into it.
We broke in this complex academic paper down into 4 highly digestible steps. First up, the Fabric deployment problem. Then, meet the metamodel. Third, the Fabric Network Orchestrator. And finally, putting it to the test.
Section 1. The Fabric deployment problem, or as I like to call it, the deployment trap. Let's dive into why enterprise blockchain setup is currently just so incredibly frustrating for developers. To set the stage here, take a look at how blockchain has evolved. It started way back with Haber and Stornet as 1991 cryptographic timestamps, going all the way to the launch of Hyperledger Fabric in 2018. The early days, they were really all about establishing decentralized consensus, like Nakamoto's Bitcoin in 2008, and then Vitalik Buterin brought us smart contracts with Ethereum in 2014. But 2018? That was a massive pivot. Hyperledger Fabric emerged, driven by IBM and the Linux Foundation, simply because enterprises needed something fundamentally different from public, anonymous networks. They needed governance, and for sure, they needed privacy. And that brings us to the core issue. Fabric gives us incredible privacy and governance, but man, it comes at a steep cost. Unlike Ethereum's super easy, fast local setup using tools like Ganache where everything is permissionless, Fabric forces you to manually manage an absolute beast of a network. Because every single participant has to be identified in a permission network, you are suddenly responsible for manually orchestrating this entire identity and consensus backbone. We're talking certificate authorities, orderers, peers, the whole shebang. It's a massive heavy lift just to get a basic prototype off the ground. Look, we all know the pain of running a shell script for, 20 minutes, only to find out it failed right at the very end. The current tools trying to solve this, like Fablo or the Fabric Test Network, kind of force you into a compromise. They either limit your customization just to make things easy to use, or they completely lack the formal semantic validation you need to catch errors early. What this ultimately means is that when you try to transition your experimental prototype into a production-ready architecture, you get entirely bogged down by deep shell script expertise instead of actually focusing on your smart contracts.
Moving on to Section 2. Meet the metamodel, aka the blueprint. Let's see exactly how the researchers solved this friction.
So, what does this all mean? Well, think of this declarative taxonomy metamodel as a giant architectural blueprint. It's a formal specification that perfectly maps out all the structural and semantic relationships among your network components, completely independent of the underlying implementation. It establishes the rules of your network before a single container is spun up or any code is actually run. You're simply declaring what the network should look like, rather than relying on hope and 20 different fragile shell scripts to build the thing.
Right at the foundation of this metamodel is the config entity. Instead of scattering your configuration across multiple, obscure files, this root entry point clearly defines your target output directory and the name of your Docker network. It's clean, it's centralized, and honestly, it's incredibly straightforward.
Building outward from that configuration, the metamodel elegantly categorizes the actual network participants. On one side, we have the organization entity. This manages identity attributes, like domain names, the number of users, and whether it acts as the bootstrap node. On the flip side, we have the peer entity. Peers belong to organizations, and they are the actual workhorses. They host the ledgers and execute the smart contracts. And notice the as-anchor attribute there. It perfectly captures the specific role of an anchor peer in cross-organization communication, all defined cleanly right in the model.
Now, the absolutely crucial point here is how versioning is handled. In traditional setups, managing legacy nodes and specific capability profiles can just turn into a messy, hard-to-debug nightmare. The capability entity solves this by centrally managing versions, think v2_0 or v3_0, across the 3 main layers: the channel, the orderer, and the application. It establishes strict boundaries around functionality and version compatibility right out of the gate.
And all of those structural rules we just talked about, they boil down to a simple, super clean YAML file format, or JSON, or TOML, depending on which side of that particular holy war you fall on. By encoding the metamodel this way, developers can replace literally thousands of lines of complicated, manual, binary configuration and disjointed environment variables with just one highly readable declarative file. It's a real game changer.
Section 3, Fabric Network Orchestrator, bringing it to life.
Now we get to the really exciting part, how we actually turn that declarative metamodel into a working network. The execution path for the Fabric Network Orchestrator, or FNO for short, is an operating system agnostic command line tool. And here's the best part. It relies entirely on containerized execution. That means it requires absolutely no external Fabric binary dependencies to run. It bridges the gap directly from your specification straight through to validation, artifact generation, and final network deployment.
Let's walk through the 4 practical steps of this workflow. First up, you write your specification. Second, and this is really where the magic happens, is validation. The tool systematically checks structural, semantic, and versioning constraints before anything else happens. Only if that passes do we move to step 3, artifact generation, where it automatically creates your Docker Compose files and cryptographic materials. And finally, step 4 is deployment. Because of that rigorous step 2, your deployment is practically guaranteed to be an error-free launch. Let's talk a little more about that validation step. Because FNO enforces consistency up front, you are never again going to waste 20 minutes deploying a network that was doomed to fail from a simple typo. It strictly enforces that you only have one single bootstrap node generating the Genesis block. It ensures all your channel names are unique, and it checks that your component versions are actually compatible with your declared capabilities. It's kind of like having a Hyperledger Fabric expert reviewing your architecture before you even hit launch.
All right, section 4. Putting it to the test, the stress test. To prove this isn't just academic theory, let's explore exactly how the researchers rigorously stress-tested FNO. The researchers didn't just test the happy path here. They ran exactly 8 distinct case studies, purposefully dividing them between perfectly valid configurations and intentionally broken ones, just to see if the orchestrator would flinch.
The data from the paper tells a really clear story. Cases C1 through C4 represented complex, valid scenarios. We're talking multi-organization consortiums, multi-channel networks, and cross-version deployments. And guess what? All of them generated their artifacts and deployed flawlessly, without a single manual adjustment. On the flip side, cases C5 through C8 were intentionally fed invalid parameters. In every single invalid case, the orchestrator successfully blocked artifact generation and deployment, instantly throwing an error. These blocked cases are exactly the kind of silent, deployment-breaking errors that developers just hate. For example, in C6, a developer tried to use a legacy 1.4 peer in a network that required 2.0 capabilities. Usually, you wouldn't find that out until the containers actually crashed. But FNO? It automatically caught it and reported it instantly. It also caught a typo referencing an undefined org3, flagged duplicate names, and even stopped a profile that totally forgot to include an organization entirely.
As the researchers summarize, by leveraging a formal metamodel, you can successfully generate and deploy networks without requiring manual adjustments. The days of painstakingly matching container ports and fixing shell scripts by trial and error are, genuinely, over.
The technology has finally caught up to the ambition of the developers. So, if you no longer have to spend your days debugging complex shell scripts and manually managing node binaries, what incredible enterprise blockchain will you build next? Thank you so much for joining me for this explainer, and I'll catch you in the next one.